Hello, everyone. Welcome to Apex Academy. And today we're going to be looking at our second weekly problem. And the problem is a old FXMA test exam problem. And the idea is not to use any calculations, but rather use physical picture or thought experiments to solve the problem by eliminating the incorrect answers. So I'll read the problem first. The Young's modulus, E, of a material mirrors how stiff it is. The larger the value of E, the more stiff the material. Consider a solid rectangular steel beam which is anchored horizontally to the wall at one end and allowed to deflect under its own weight. The beam has length L, vertical thickness H, width of W, mass density of rho, and Young's modulus E. The gravitational acceleration is G. What is the distance through which the other end moves? So when you read a problem like this, by the way, the test already give you a hint that you should eliminate implausible answers. And Apex, as we give you a further hint that you should use qualitative analysis instead of the quantitative analysis. What I mean by that, I'll give you be more explicit in a minute. But the idea is you're given a new physical quantity, which is Young's modulus. The first thing to think about is do not panic. It's something we will not be learning in any of the courses, but that's okay. It's very often for FXMA test to give you something that's not introduced before, but you can still use the definition they will give you. So in this case, the Young's modulus E is nothing but to measure the stiffness or how rigid a material is. And so the more rigid, and of course it's intuitively, it's less easy to bend, right? So that's the idea. Okay, so let me put on some graphs first that helps us to get started. Here's a wall, okay, and here is our beam. And because of its own gravity, as I already said in the problem, it's going to bend, right? They call it deflector, same thing. It's almost like a long tree branch and always bending down towards the ground. And the reason of that is, of course, gravity. So gravity G is over here. And as stated in the problem, the length of this is L, okay? And the vertical thickness is H, and the width is W, but we will have to go to a cross section to look at directly look at the direct cross section to look at the width. So I'm gonna, in that case, let me draw. This is a wall, right? So I'm looking towards the beam now, and I have the beam starboard over here, okay, and it's gonna be bending down because of its own gravity. Like this, because it's going to bend down, right? Okay, oops. I don't like my drawing, so I'm going to erase this a little bit. And so I'm going to, oh, okay, I need to remove this automatic shape thing here. All right, so it doesn't autocomplete for me. All right, so the other side is going to look like this. Okay. This. So it's going to be bent down and okay, so this is the beam from the cross section direction. Okay, and W is this distance over here. Okay, So this is our situation. It's nothing but a tree branch that's bending down towards the ground. So let's think a moment without calculation, what could happen? Suppose we measure the amount of deflection, okay, is D. All right, so the amount of deflection is D. Let's think about what could change D. Okay, everything is about gravity, right? So this tree branch is only bending, or this steel beam is only bending because of gravity. Therefore, if G is 0, if we're putting this on a spaceship, there should be no bending at all. Therefore, D is going to increase if G increases, and D would be 0 if gravitational constant is 0. Okay, so that is one thing to think about. What caused the beam to be deflecting. Well, the second thing is this is very intuitive. You can make cut a piece of paper and look at the how long by changing the length of the paper and just observe the tree branches in the backyard. You should see that the longer the branches, the more deflection it bends, right? So therefore, we should also expect D is increasing if L increases. Okay, that's a second idea that you can, without doing any calculation, you can this common sense from daily observations. And the third thing is, regard of the vertical thickness, it will decrease if H increases. And this is very easy to test as well. If you find something that's very thin, and of course it's easier to bend than something that's thicker, right? And that thickness is primarily based on the H. And again, you can easily do experiment using a piece of paper and cutting the width of the thickness of the paper or cardboard and see how that varies. So without doing any calculations, this is what I expect. And finally, D would decrease if the Young's modulus increases. Okay, the reason is the stiffer the material is, the less it's likely to be bent. That's why you want to use a steel to build like hanging structures instead of using a rubber, right? Which will be more likely to bend, deflect. Okay, finally, the relation with W. Okay, so if you look at the W, the effects of W, we gotta or the width, we should look at this figure over here. And I want to draw a new line right in the middle. Okay, all right. And if you look at this, you can basically cut this beam hypothetically into two halves, right? Each of them has a width of 1/2 of W. And because they are going to be having the same bending, because you just hypothetically cut them in half. So you can move these two parts apart or combine them together, or moving them very close and they're almost touching and it looks like if it's a single beam. But in either case, this argument is that when you double or half the width, it is not going to change the amount of deflection with everything else fixed. Therefore, you expect D is independent of W. Okay. Now you put everything in this thought experiment together. Now let's check all the answers. Okay. First of all, let's look at A. So in the case of A, well, in the case of A, it's independent of W, right? It's independent of W. That checks out. And the issue is when H increases, D also increases. So that's incorrect because, as we said, H and when H increases, you actually want this thing is going to be less deflective, and that's common sense, right? You have a thicker tree branches versus a thin tree branch. Of course, the thicker tree branch will be deflecting less. Okay, and let's look at the B. Well, the issue with B is that, again, as H increases, the deflection also increases because you're increasing because that is how the denominator is H squared. So that's incorrect. Okay, and let's look at C. Okay. Well, C is independent of W. That's good, and it checks out with the issue with it looks good for increasing L. It will give you a increasing deflection. However, same issue tells you that when H increases, if you look at the C, that also leads to increasing D. So that's incorrect. Okay. And let's look at the D. Okay. Let's look at the D. Well, D checks all the marks, right? So you see when L increases, it increases the deflection. And look at the numerator first. And when G increases, when gravitational acceleration increases, let's say, for instance, you put this thing on the Mars, which has less G, you would have less deflection. You put it on a spaceship, you have very little G, and you have very little deflection. So that all checks out in D. And also, it's inversely proportional to Young's modulus and H squared. So that means when you increase the stiffness of the material or increase the thickness of the material, it will be less deflective. So that checks out, right? And let's look at the E. Okay. Well, the problem with E is when G decreases, D increases. That's incorrect because, as we said, assuming you put this beam on a spaceship where there's no gravity, then you would expect the beam will stay straight, no deflecting at all, right? So this is incorrect. So by looking at all these possibilities, you can easily, very quickly pick up the correct answer, which is D. And so this is a kind of a problem I really like because what it relies on is not a mathematical calculation, but rather if some increasing or decreasing the qualitative analysis that we typically say, and a lot of thought experiments, right? The thought experiment is how you assess your physical picture. How good are you as a physicist? Think as a physicist is you can do a lot of thought experiments. Without doing actual experiment, you can do thought experiments and see what are the possibilities. Okay, so and how do you build the physical pictures? Well, many things, but in our course, we focus on building the very strong concept foundation. So you start with the right concept, and we're going to gradually introduce more and more real life, daily life associated examples. That's how we build physical pictures. You can only build that through learning. Okay, hope you enjoy this interesting problem, and thank you again for looking at our solutions.